Okay, physics. So I want to talk with you about Atwood machines and half-Atwood machines and get you to think about them. The principle is going to be the same as what we've seen before, but sometimes it helps to go through these in a little more detail because they tend to freak people out. So this is what an Atwood machine looks like. So in this case, it has two pulleys. I could do this. There's one pulley, but the pulleys in this case are massless and frictionless, which means that the tension is going to be the same everywhere across that green wire. So really important here. So later on, we will give mass to the pulleys and we will give friction to the pulleys if we want to. So we will make it a little bit more complex, but for now, let's just stick with a simpler situation. So what you'll notice, so if I start this simulation in motion, what you'll notice is the heavier mass is going to fall and the lighter mass is going to rise. So this is one key. So one of the keys to solving these problems is deciding what the direction of motion is and setting your axes to be consistent with that. So the curious thing is that the direction of motion for the large mass is in the direction of gravity, and for the small mass, the direction of motion is opposite gravity. So we're going to give gravity two different directions for different masses. So a little bit tricky. Anyway, but out of this, you should get something that you expect, right? So you're going to get a curve on a displacement graph indicating there is acceleration, and you will get increasing velocity, and from that you can get acceleration. And usually this is what we're headed after. So how do we get to acceleration? We can get there two ways. One, if we look at the position. Second way we can get to acceleration now is through forces. So let's do that. So the idea is going to be the same, that we're going to make free body diagrams for one mass, a second free body diagram for the second mass, and then a third free body diagram for my whole system. So let's go through and take a look at what that's going to look like for this. Here we go. Okay, so there we go. Now we can see this. Again, here's my system. I've got two pulleys and two masses. I'll call this M1 and this one M2. So conceptually, I know that M2 is going to fall, so I'm going to make my direction of motion this way. So I want to make anything in the direction of motion positive. So notice what happens here, right? Gravity is positive in this direction, but on M1, gravity is going to be negative, and this is the key to the whole thing. So I'm going to set my direction of motion as being positive. And I'm going to draw my three free body diagrams. So for M1, what am I going to have? So I'm going to have gravity going down. I'm going to have tension pulling up. And those are not going to be equal, right? So it's accelerating. So it's experiencing a net acceleration. If it's stationary or constant velocities are going to be equal. So for mass 2, what do I experience? Well, I'm going to have gravity going down, and I'm going to have tension going up. Notice, though, that what I'm doing here, so I'm saying this direction is positive for this mass, and this direction is positive for this mass. Really important. So sometimes we just like turn it all sideways. So if you wanted to, I could rewrite this and say, well, here's M2. It's connected to M1 and is moving in this direction, right? So conceptually, it's the same thing, and then I can draw free body diagrams, and I'd have my same an easier axis to deal with, right? So either way, you've got to get this sorted out. So I have to use the same orientation for my positive and negative signs, and the pulleys trickify things. Is that a word? So they make it trickier so that the pulleys change the direction of the force. So I have to change the direction of motion. So. Okay, I'll make one for my system. What's my system going to be? Well, acting in the direction of motion. I'm going to make a direction of motion downwards. Why not? Acting in the direction of motion, I'm going to have M2G. And acting opposing the direction of motion is going to be M1G. And those are the only two external forces. Notice my tension is going to cancel. So what is my net acceleration? Well, my acceleration of my system is kind of easy to figure out. So I said this is positive, so I'm going to have M2G minus M1G over, what is it? It's going to be the mass of my system, which is going to be M1 plus M2. And this is the classic equation that we get to for an Atwood's machine. So a few different ways to go about getting that, but it's probably easiest from a force diagram of the whole system if you're careful about it. Okay, again, these things are connected, so the acceleration of my system is going to equal the acceleration of mass 1. It's going to equal acceleration of mass 2. I just have to be careful about the signs of things. And I can do a force diagram. I can figure out the tension here, or whatever it is that I need to know. This is the key to dealing with Atwood machines. So again, I'm going to make a free body diagram for each mass, and then an extra free body diagram that's going to show my whole system all together. And direction of motion is important. So there's a second type of Atwood machine, which we call a half-Atwood machine. So it's going to look something like this. So the half-Atwood machine is going to have one hanging mass, and then something on a table. In this case, I think it's a puck that's designed to be frictionless. But what's going to happen? Well, you can make a prediction, right? So my mass is going to fall and my puck is going to accelerate. Well, they're both going to accelerate at the same rate. But again, what do I have? I have one force that's driving that. In this case, the driving force for that is going to be gravity. But that force of gravity has to drag the inertia of the puck as well as the inertia of the mass. So it's not going to accelerate at the rate in free fall. It's not going to accelerate at 9.8, but it's going to be affected by dragging along the other masses. So let me take a look at what this one looks like. It's going to be the same thing. So we're going to draw free body diagrams and make an extra one for our system, and it's all going to sort out wonderfully. So we're going to show this. Okay, so here we go. So we call this a half-Atwood machine, right? So I've got a pulley, some sort of mass. I'll call this M1, going over a pulley, and I have M2, taller Lego, and it's going to fall, right? So first thing I'm going to do is I'm going to say, what's my direction of motion? If I wanted to, I could redraw this in a straight line. This is M1 being dragged by M2, that's a 2, and this is being pulled by some force, right? This is going to be the force of gravity acting on this one, right? So I have linked boxes, if you want to think of it that way. But I'm going to set my direction of motion as being positive. So in this case, my horizontal direction is the direction of motion. In this case, my vertical direction is the dimension of motion. So what happens at M1? Well, in my direction of motion, I'm going to have this force, which is tension, which is going to be pulling it. If it's frictionless, then that's the only force, right? I'll have horizontal, vertical forces, they will cancel. So I'm just going to have tension acting on M1 when it's frictionless. M2, here's M2. M2 now is going to have this gravity pulling it down, and it's going to have tension pulling it up. Those are not equal because it's accelerating. And then for my system, altogether, what am I going to have? Well, I'm going to say this is the direction of motion of my system. So this is going to be driven by M2G, and that's it, right? So I have one unbalanced force. Again, I can use Newton's second law, so the acceleration of my system, often an easier place to start. So acceleration of my system is going to be the sum of the forces of my system, which is just M2G, which is in the direction of motion. So I'm going to leave that positive. And then I'm going to divide that by the sum of my masses, which is going to be M1 plus M2. So for a half-Atwood machine, it looks like this. So remember, the Atwood machine had a similar but slightly different formula. So the full Atwood machine, the acceleration of my system was the larger mass minus the smaller mass times gravity over the sum of the masses. Right? So remember, one's fighting it, right? So in this case, my smaller mass and my full Atwood machine is fighting it. So that's consuming some of the force. Here, all of that force of gravity is going into accelerating my system. It's got to get those two masses moving. It's got to overcome the inertia of those two masses. So that's taken into account in the denominator. Here, that net force of gravity, right, is the external force that's driving the system, and that force that's driving the system has to move both those masses in the direction of motion. That's the plan. So Atwood machine's not too tricky once you get a handle on it. And again, 3 diagrams. So one for each mass and then one for the system. And then we just Newton's second law the heck out of it, and it all works out. Hope that helps. Talk to you soon. Bye.